So welcome everybody. Congratulations on making it to the last week of the semester. Our commiserations, and we still have a final presentation and exam for any of your classes. But science never ends, and we are lucky enough today to bring us out into the break. They have Dr. Tarraneh Eftekhari from that work at the University of New Mexico, and then moved to Harvard University, where she got a PhD with Ida Welcome. She was then briefly a CNF fellow at Northwestern before moving to an Einstein Fellowship, which is her current position for the next few years. She's part of the FO collaboration with these things called fast radio bursts, which is what you'll hear about all day. This isn't a topic that's actually new for us. We were lucky enough to have her come down to Transient University this summer, and like all great talks, it left me wanting more, having more questions. And so I realized that as colloquium chair, I could keep it first. So
great. Thank you so much. Well, it is great to be here today. Thank you all for having me. I've enjoyed meeting with people throughout the day, talking about science, and also just learning about your department, which has been a real pleasure. So today I do want to talk about fast radio bursts. So this is a relatively new field in astrophysics. The title of the talk is maybe a little bit misleading. By the end of the talk, I won't be able to tell you exactly what it is that produces FRBs, but hopefully I will shed some light along those lines and really just highlight the significant progress that's been made in a relatively short amount of time, as we'll see. And then in addition to FRBs, so I work on transients pretty broadly. So I will talk about some other work that we've been doing towards uncovering new populations of radio transients. So I'll spend some time talking about that towards the end. Okay, but starting with fast radio bursts, I want to start by pointing out that the origin story for FRBs is actually not too dissimilar to the one that we saw play out for gamma ray bursts. So GRBs were first detected serendipitously in the 1960s. The US had launched a series of satellites into space designed to detect the testing of nuclear weapons by the Soviet Union. And what they detected were actually the first cosmological gamma ray bursts. So these were eventually declassified a few years later and published in this famous paper by 3 scientists at La Salle National Labs. And then it would actually be about 20 years before any significant breakthroughs were made in the field. And that's because gamma ray instruments at the time had these large positional uncertainties. And so it was really challenging to say much about gamma ray bursts outside of their very short duration gamma ray emission. So that finally changed in 1997 with the detection of an afterglow from a long GRB. And so this was the first time that we could pinpoint one of these events precisely to a host galaxy and obtain a redshift measurement. And taken all together, the properties of the host and the afterglow pointed to the core collapse of a massive star as the progenitor. And then similarly in 2005, X-ray follow-up of a short GRB led to the discovery of an X-ray counterpart and a precise localization for that event. And then, of course, in 2017, short GRB was associated with the binary neutron star merger, which I'm sure everyone's familiar with. This is a GW170817. And this provided direct evidence that at least some short GRBs are produced in these mergers. But what I really want to emphasize here is that it's these localizations that were really key when it came to making progress in terms of understanding GRB phenomenon. And that's because you need a host association in order to understand the distance scale and hence the energetics, as well as the environments in which these events reside, right? But you can see that it took about 30 years in this case before we were really able to achieve such localizations and start to make significant progress. Okay, so the story of fast radio bursts is actually not too dissimilar, although it does evolve at a much more rapid pace, as we'll see. In many ways, this is probably a reflection of the rate at which technology is advancing. So the first FRB was discovered in 2007 by Professor Duncan Lorimer and his student. And what they were looking for were pulsars. So they were using this telescope here. This is the Parkes Radio Telescope in southeastern Australia. It's this huge 64-meter dish. You can actually see this building across the face of the telescope there. So as I said, what they were looking for were pulsars, but instead what they found was this extremely bright, only 5 millisecond duration burst. And unlike pulsars, which repeat with a very regular cadence, this was the one-off event. And the other thing that was really unusual about this event was its large dispersion measure. So when we observe pulsars or FRBs across some finite bandwidth, we see that the low frequencies arrive with some time delay relative to the high frequencies. And this is really just this happens as the pulse travels through some cold plasma, right? And it's effectively just a measure of the integrated column density along the line of sight. So as I said, this is a common characteristic for pulsars, right? We see this anytime we see this dispersive sweep, anytime we observe a pulsar. And in fact, there's been some really nice work using the dispersion measure of pulsars to map the electron content of the Milky Way. So in many cases, we have independent distance measurements to pulsars. And so we can use their dispersion measures to map the amount of electrons along a given line of sight. This map here is showing contours of constant dispersion measure at a galactic latitude of 0. You can see the spiral arms here, the solar system here. But we actually have a really nice 3D map of the entire Milky Way. And so what this tells you is for any given line of sight through the Milky Way, what the electron column density is along that particular sight line. So in the case of the Lorimer burst, this first FRB that was detected, it had a dispersion measure of 375. And for that particular sight line through the Milky Way, the contribution from the Milky Way galaxy was only 25. And so right away, this is telling you that there have got to be many more electrons between you and the location where the FRB originates. And in fact, we attribute most of these excess electrons to the intergalactic medium. At the time, our sort of best estimate models imply this relation here, where the redshift scale roughly is dm over 1200. And so this would imply a redshift of about 0.3 for this particular burst. Even once you subtract off the Milky Way contribution, right? Which in this case is quite small. It is worth noting, however, that this redshift estimation is just an upper limit. So there are actually a few different components that contribute to the observed dispersion measure that we get for an FRB. So in addition to the Milky Way and the intergalactic medium, you might also expect a contribution from the host galaxy of the FRB itself. And then if whatever is producing the FRB is enshrouded in some kind of dense material, so for example, supernova ejecta or dense nebula, you might expect some kind of contribution from that as well. So this kind of illustrates the whole idea. The FRB originates in some distant galaxy. It passes through a nebula in its immediate vicinity, passes through any material in its host, through the intergalactic medium, and then finally through the Milky Way galaxy. And it is really just this Milky Way contribution that we know a priori, as I mentioned. We think we have a pretty good handle on the IGM contribution as well. And excess is generally attributed to the host and very local environment around the FRB. So for this particular Lorimer burst, even if we place it at roughly half of the distance based on this inferred relation here, and I see there's a typo there, the energy comes out to about 10 to the 40 to 10 to the 41 Earth. And just for comparison, the most luminous giant pulses from the Crab pulsar, these so-called Crab giant pulses, have energies of about 10 to the 31 Earth. And so we're talking vastly different energy scales here. Okay, so the dispersion measure gives us this kind of rough proxy for distance. This is very unique to FRBs, right? We don't have this information for GRBs, for example. But without being able to pinpoint precisely where on the sky the FRB comes from, we don't know exactly how far away it is, and we don't really know what kind of environment it lives in. And for the first decade or so of FRB detections, most FRBs were detected with these very large single-dish telescopes. So in addition to the Parkes telescope, we had detections with the Green Bay telescope in West Virginia, as well as Arecibo, before it was sadly decommissioned in 2020. And just to give you a sense of the scale of the problem, here is what the Arecibo localization region looks like over the Hubble Deep Field. So you can see that even within just a few arc minutes, the number of galaxies is so large that it is virtually impossible to say with any level of confidence which of these galaxies your FRB comes from. So we kind of highlighted this issue back in 2017. There's a lot going on this figure, so I'll walk you through it. On the y-axis, we have galaxy brightness, where brightness is going to be increasing towards the bottom. And on the x-axis, we have the size of your localization region, okay? These black curves here correspond to the probability that a galaxy is in your region purely by chance. So the smaller this number, in other words, moving inwards towards this region here, the more confidently you can associate a host with your FRB. Okay? And what we showed at the time, as I said, most existing FRB detections were done with these single dish telescopes. And so you're sitting in this regime where you can't make confident associations, right? So this was really the challenge that we were faced with. And in fact, we showed that you really need localizations at the level of about 10 arc seconds or less in order to identify your host galaxy. And this band here just corresponds to the luminosity of a typical L-star galaxy over the redshift range, 0.1 to 1. Okay, so that was more or less the state of things in 2017. Just a decade after the first FRB was detected, we had this growing sample of events.
You have a question from Brian Fields online. Brian, do you want to unmute?
Yeah, so this is great. But when you mentioned the constraints on energetics, was that assuming that the burst is isotropic?
Yes, it is.
Yeah, great. Thanks.
Yep. Okay, so yes, this is the state of things in 2017. We're starting to build up this much larger sample of FRBs, but we're still using these single dish telescopes. And so we're really not able to localize them on the sky. Now, just a year prior to this event, however, we had the first detection of a repeating fast radio burst. So prior to this, all events were detected as one-off events. So despite many hours of follow-up of the same region of the sky, we did not detect any repeat bursts. Now, in this particular case, we did detect 10 repeat bursts from the same direction on the sky. And importantly, they all had the same dispersion measure. So here you can see all of these bursts, where in this case, the dispersive delay that I mentioned has been removed from the signal. So this was really exciting at the time, right? The first time we have a repeating FRB. And this also kind of upended these cataclysmic progenitor models. Because in this case, you need your source to survive in order to continuously generate bursts. And even more importantly, the fact that it repeated enabled an interferometric localization with the very large array. So here you can see these large circles, or those Arecibo 3 arc minute localization regions. And you can see a small here, which is actually the FRB that's detected in fast sampled imaging with the VLA. You can see the dispersive sweep from the pulse here, and then the de-dispersed time series once you correct for that sweep is often. So if we come back to this image here, this VLA localization took us from the 3 arc minute region down to this sub-arc second position here. And in this case, the FRB turned out to be pretty much right on top of a low luminosity dwarf galaxy, which you can see as a little faint smudge there. And then in addition to the host, it was coincident with a persistent source of radio emission. And that's what you're seeing in the box right here. So we have these bursts that seems to be repeating, no periodic nature to the bursts. We do detect, a handful of bursts. And then we also have some longer-lived quiescent radio source that is coincident with the burst. So following this discovery, Brian Metzger and others actually pointed out the similarities between this host galaxy and the hosts of two other types of transients. So these are the so-called superluminous supernovae and long gamma ray bursts. These transients are believed to be powered by magnetars. So you can think of these as basically pulsars with beefed up magnetic fields. And what they showed is that the properties of these transient host galaxies are actually remarkably similar to this host galaxy where the FRB was located, right? And so this is kind of hinting at similar stellar progenitors. Okay, so here we are nearly a decade after the first FRB was discovered. And we have the first localized event. So this gives us definitive evidence for the first time that FRBs do in fact come from cosmological distances. And the fact that the host was a dwarf galaxy was a bit surprising. So dwarf galaxies account for less than a few percent of the total stellar mass in the local universe. So if FRBs trace stellar mass or the cosmic star formation rate, you instead expect to find them in much more massive galaxies, right, where the bulk of star formation is happening. And so at face value, this is kind of pointing towards some perhaps exotic progenitor channels. And in fact, for several years, this was really driving our theories of FRB progenitors. But as we'll see, we then start to associate FRBs to much more different types of galaxies. Okay, so fast forward to today, there have been over 3,000 FRB detections. And of those, only about 50 or so are found to repeat, so a very small fraction. And only about 50 have been localized to their host galaxy. So the vast majority of events, we have not been able to pinpoint their host galaxies. And what I hope to convince you of for the rest of this portion of the talk is that it is these localized events that really kind of provide the key to unlocking FRB progenitors. And this was really similar to the way that we saw this play out for gamma ray bursts, but you can see that the field has already evolved at a much faster pace. So this plot here just shows the number of FRB detections per year. And there's this huge spike here thanks to the CHIME telescope in Canada. So this is the Canadian Hydrogen Intensity Mapping Experiment. It consists of these 4 long cylinders, and the sky basically just transits over the telescope daily. And so they're really kind of paving the way in terms of FRB detections. And here we have the number of articles that contain the word fast radio burst in them. Since 2013 is actually when the term was first coined. And I would say in 2017, there were more theories for FRBs than there were FRBs themselves. Luckily, that is no longer the case, but that was really the state of the field at the time. And in making these talks, I realized that this slide here that was compiled just a year ago is now entirely out of date. So as I said, this is just CHIME detections. We have about 4,000 detections with CHIME. So, in the last year, it's just absolutely exploded.
So I hadn't appreciated there were that many that were well localized already. Is there, because there's now 50 of these repeating FRBs, presumably, that are well localized?
Oh. No, so that's a bit misleading. So there are 50 repeaters and there are separate 50 that are well localized.
I see.
So of the localized, it's maybe 5 or 6 repeaters.
Okay. So this may be less applicable then, but of the repeaters, is there any statistical difference between the dispersion measure and the non-repeaters?
Not of the dispersion measure. There are some interesting differences in other properties. So for example, the scattering timescales and the bandwidth. Okay. There are some statistically significant differences there. That's a bit interesting. However, there are some other papers that are able to kind of reconcile those differences with a single population. So, yeah. Okay. So just a quick recap of FRB properties. These are very short duration bursts of radio emission. The inferred all-sky rate is something like 1,000 FRBs per sky per day. There seems to be this dichotomy between repeating and apparently non-repeating events. So perhaps they're distinct populations, but as I just mentioned, perhaps they're all the same, and we're just detecting the brightest one-off events, but they might be repeating sort of under our detection threshold. In terms of their morphologies, they're also kind of all over the map. So some exhibit this scattered broadening in the tail. This tells you that the pulse has undergone multi-path propagation. We see this in some FRBs, but not all FRBs. And then finally, their energies span many orders of magnitude. And so you need any kind of emission mechanism to be able to reconcile this very wide range in energies.
What's the variance in the brightness of each?
That is a great question, and I don't know off the top of my head. Yeah, so there's been some work looking at the luminosity function. Actually, I'll show a figure later that will show how many orders of magnitude a single repeater can span. Yeah. Okay. So why are localizations so important? So by localizing FRBs and constraining their redshifts, there's really a whole host of science that opens up to us. So this spans kind of cosmology studies to the host demographics, of course, and then also how can we connect FRBs to other classes of transients, for instance, through multi-wavelength counterparts. So one could spend an entire talk focusing on any of those subjects, but as I said today, I really want to talk about how their host demographics can inform their progenitors. So a lot of the work that I'll talk about today is work that's done within the F to the 4 or fast and fortunate for FRB follow-up collaboration. So the way that F4 works is we partner with a number of FRB discovery experiments to conduct follow-up of well-localized events, right? So typically an FRB is detected to within a few arc-second precision with one of these experiments, and then we trigger a whole host of both ground and space-based telescopes. And now this is not only to study the host galaxy and obtain a redshift, but also to search for multi-wavelength counterparts, which I'll talk a little bit about. So this is our team today. We have 4 team leads, which are professors sort of spanning institutions, a small number of postdocs, and then quite a few students who are actively leading projects. And I'll highlight some of the work that they're doing today. Okay, but I want to step back for a moment to really emphasize the utility of these host galaxy studies when it comes to transients. This type of analysis where we look at the global properties of transient hosts in order to understand their stellar populations actually has a really long history in the field of transients, right? And I kind of alluded to this earlier in the context of gamma ray bursts. But the idea is that if we look at the landscape of various types of transients, one way to think about them is in terms of the ages of their stellar progenitors and how that then connects back to their host demographics. So starting at the very youngest end, we have these very young, very massive O-type stars. These collapse and give rise to jetted explosions. So things like superluminous supernovae, long GRBs, type 1b supernovae. And these transients tend to preferentially live in ultra-star-forming galaxies and dwarf galaxies. So things that are sort of on or just above the star-forming main sequence, where you might expect these very massive stars to reside. Moving along in age, we have more normal B-type stars that have retained their hydrogen envelopes. These collapse and give rise to ordinary core collapse type 2 supernovae. And these occur in fairly typical star-forming galaxies. Then we have things like binary neutron star mergers, binary black holes, or neutron star black hole systems. And here, the progenitor age is governed by what's called the merger delayed timescale, right? So how long does it take for these two objects to come together and merge? And that's actually why you end up with kind of a wide range of progenitor ages. So these objects merge and give rise to transients like short GRBs or the compact object mergers that are detected with LIGO. And they tend to arise in kind of the full range of galaxy types, right? So both star forming and quiescent. And this really reflects the wide range in ages of their progenitors. And then finally, we have things like degenerate white dwarf systems. These can give rise to type 1a supernovae, or the so-called calcium-rich transients. And these also occur in both star-forming and quiescent galaxies. We ultimately want to answer with FRBs is, where do their host galaxies lie within this landscape, right? In other words, what types of stellar populations are driving FRB production, and how do they connect back to other types of transients? So as I said, the current sample of FRB hosts includes about 50 or so published events. So despite the fact that we have over 3,000 FRB detections, it's still a very small fraction that are small enough, are localized to a small enough precision where we have a host. But one of the key results from these localized events thus far is that there's a really wide diversity in host types, and that the dwarf host galaxy of the first FRB is not representative of the norm. So I mentioned that dwarf galaxy kind of pointed to very rare formation channels, right? Because it's sort of not the typical environment that you might expect to find an FRB or any source for that matter. And in particular, it kind of suggested that FRBs might come from young magnetars that are formed in superluminous supernovae and long gamma ray bursts. And part of that idea was really the fact that all of these transients share a preference for these low luminosity dwarf galaxies, right? And in fact, just last year, there was a second repeating FRB that was localized to a dwarf galaxy. And like the first one, it was also coincident with a persistent source of radio emission, right? And so this might suggest that at least some subset of FRBs are produced through these more exotic channels. So as I said, these were both coincident with persistent radio sources. This is something that we've not yet seen for any other events outside of these dwarf localized events. But basically, as I said, in addition to the bursts themselves, we see this much longer-lived persistent radio emission. And the prevailing theory here is that the radio emission is coming from some kind of magnetar nebulae. So you have your magnetar, which releases a relativistic outflow of particles. And this is what's powering the observed radio emission. You can see the spectral energy distribution for one of the sources seems to match decently with one of these models. And so for these two particular events, you can reconcile the repeating nature of the bursts, their dwarf host galaxies, and these persistent radio sources with this model in which FRBs come from young magnetars. But based on this much larger sample of FRB hosts that we're now starting to amass, as I said, we now know that FRBs also reside in much more massive galaxies. Dwarf galaxies are not ubiquitous. And that tells us that these exotic channels are not the dominant formation mechanism, right? So these young magnetars can't really explain all FRBs. But that being said, it is actually quite common in the field of transients to evoke magnetar progenitors. So separate from the young magnetars that we think are powering these sources, you can also get sort of typical magnetars. Yes?
So we get to young or old. What kind of
I mean, that's a great question. And I would argue, so probably something very similar to pulsar emission. And I would actually argue that we like pulsars, we'll probably never know. That's my maybe pessimistic take. But the mechanisms are like synchrotron maser emission, for example, some kind of coherent emission mechanism.
So if you go back to your previous slide, it's true that okay, so these are not all in dwarfs, but you do have nice resolved images of the galaxy, and what matters is presumably the stellar population at the location of the FRB. Is that similar between these different galaxies?
No, as we will see. Yes. Short answer is no. Longer answer is we don't yet know, because we only have such high resolution observations for a small sample of events. Okay. Yeah, so the takeaway here is that you can get different types of magnetars from different classes of transients. And this really just highlights that how we connect FRBs to magnetars really depends on the stellar populations within their host galaxies, right? Okay, so then in 2020, we had a pretty exciting discovery that actually definitively connected at least some FRBs to magnetars. This was the discovery of an FRB-like event from a known galactic magnetar, SGR 1935. So initially the bursts were a few orders of magnitude below the faintest detected FRBs in terms of their luminosity. And so there were a lot of questions about, whether this is truly a fast radio burst. Maybe it represents the tail end of the luminosity function, and we just don't detect these at extragalactic distances because they're too faint and so on. But actually, coming back to your question, there's since been an FRB localized to M81, and it turns out that some of those bursts are even lower luminosity than the galactic magnetar. So this is a duration luminosity-based case for radio transients. We have things like ordinary pulsars down here, giant pulses from the crab here, and cosmological FRBs up here. And you can see these bursts from this galactic magnetar that sit down here, right? Well below the population of cosmological FRBs. And so, as I said, there was sort of some hesitancy to call these things fast radio bursts because of the vastly different energy scale there. But we've since, as I said, detected FRBs from M81. And because of the repeating nature of this galactic magnetar event, there are actually some bursts that are even more luminous than cosmological FRBs. So yeah, you can actually see how from a single event, albeit this is the galactic magnetar event, the energies do span several orders of magnitude there. And so I'll just say that the fact that we have this galactic magnetar event, this event in M81, is kind of hinting at a more continuous luminosity distribution between pulsars and FRBs, for example. And so maybe getting.
I can't read the lines.
Yes. Yeah.
Sorry, what? Pulsars, but that's okay. That's every pulse.
Yeah.
Pulsar. Okay, that's just the line.
Okay. So that is kind of circumstantial evidence pointing to magnetar progenitors for a few events, right? But now we can sort of step back and look at the sample of localized events thus far. As I said, we have about 50, and we can start to see how the host properties, as a whole, what they tell us about FRB stellar population. So there's been some really nice work by Alexa Gordon, a graduate student at Northwestern, where she's presented the largest compilation of FRB host galaxies, including their star formation histories. And what we see is that FRB hosts really seem to trace the star forming sequence. They span a wide range in both star formation rates and stellar masses. In terms of their star formation histories, we find that most are peaking in star formation in the last gigayear or so. And so taken all together, these properties do seem to point through magnetars formed through core collapse, right? Because again, we kind of expect these to span the full distribution of galaxy types. There is some evidence that the hosts of repeating FRBs extend to somewhat lower masses than non-repeating events, but this is very small sample size, so really not statistically significant. But you can imagine that as we move into the era of many hundreds of localized events, it'll start to become much more clear whether these two populations sort of bifurcate. Okay, from high resolution HST observations, so coming back to your question, we are finding that some FRBs are coincident with the spiral arms of their host galaxies. This is work led by Alexandra Banyan, the graduate student at UC Santa Cruz. But interestingly, these FRBs are not located in the brightest regions of their spiral. Okay. So this suggests that although the positions of the FRBs are correlated with star formation, they are not tracing the youngest, most massive stars in the galaxies, and instead are sort of tracing the normal distribution of stars. So this is just a nice case study of how we can learn about FRBs through this high resolution imaging. Yes. Well, I wouldn't say white dwarfs because it's still where sort of active ongoing star formation is happening. But it's certainly not pointing to the most massive stellar progenitors. But I'll come back to white dwarfs later. Okay, moving into the millimeter regime, there has been some work looking at the molecular gas content of FRB hosts. And what we're finding based on these very small samples so far is that FRB hosts may have higher molecular gas fractions relative to local galaxies. And this is giving us some insight into the star formation mechanism operating in these galaxies, right? The younger the stellar population or the more massive the progenitor, the more molecular gas you expect. And so at face value, these would point to massive star progenitors. But of course, we ultimately want to build up a much larger sample millimeter observation of these hosts. We can also probe star formation at radio wavelengths. This FRB here has turned out to be one of the most prolific repeating FRBs. So in just a few months, it repeated thousands of times. And this is work done by Vic Dong, a graduate student at Northwestern, using high resolution VLA observations to look at the environment around the FRB and try to understand, whether its hyperactivity could be related to its local environment in any way. So in this case, you can see that we do detect radio emission from the host. This is distinct from those persistent sources that I mentioned earlier. In this case, the radio emission is coming from the star formation within the host galaxy. And then we have these nice HST images, which actually reveal that there doesn't seem to be any of star formation at the FRB position. So despite the fact that it is this very active repeating FRB, it does not seem to be associated with a region of enhanced star formation. But the nice thing about radio observations is that they give you an unobscured view of star formation. And in this particular case, we do find that this FRB lives in one of the highest dust obscured host galaxies. Okay, so finally, in the X-ray band, we've been doing a little bit of work trying to understand the AGN occupation fraction of FRB hosts. When we look at a BPT diagram for FRBs, we do see some subset of hosts in liner and AGN regions. And for these sources in the liner region, we're particularly interested in understanding where that source of ionization is coming from, right? So is it coming from some kind of central AGN, or alternatively, is it a population of evolved low mass stars? And of course, that would be interesting because it would point to more delayed progenitors. And so the way that we wanted to get at this question is simply ask, do FRBs reside in AGN host galaxies at sort of an elevated rate to normal galaxies? So we've compiled, we got some Chandra observations and compiled existing X-ray data for FRBs based on this sample so far, we can say that most FRB, we can rule out typical AGN for FRB hosts. We do find evidence for AGN in a couple of FRB hosts. And this might have implications for FRB progenitors. So there were some theoretical papers in recent years suggesting that you can get an enhanced rate of compact objects in AGN appreciative. So again, just kind of understanding whether there's a correlation would have interesting implications in that context. And then separately, we can also look for X-ray counterparts, right? In this case, we're interested in ultraluminous X-ray sources. These were proposed as possible FRB progenitors. But what we're finding is that we're really not sensitive to the typical luminosities of ULX. And so if we want to detect these things moving forward, we're really going to have to focus on the most nearby events. Okay, so lastly, in case you guys are starting to feel comfortable about the idea that FRBs come from magnetars, I would like to make you feel less comfortable with this slide. So I mentioned earlier that there was an FRB coming from M81. And it turns out that if you zoom way in on milli-arc second scales, the FRB is actually coming from the center of a globular cluster. Now, this is strange if you believe that FRBs come from magnetars, because this is a very unlikely place to find a magnetar. And in particular, the age of this globular cluster is 10 gigayears. And so this is really challenging the notion that FRBs come from massive star progenitors or magnetars. But on the other hand, there has been some theoretical work that you can suggesting you can get a magnetar, for instance, from white dwarf mergers or the accretion-induced collapse of a white dwarf. And so these events are intrinsically more rare, though, of course. And so I'd say this is, really a bit of an open question. And it just kind of emphasizes the challenge ahead of us when it comes to reconciling these diverse environments with FRB progenitors. So finally, I'll just quickly mention that the F4 team has a couple of large programs in collaboration with both Kraft and Chime to really start and build the first homogeneous samples of FRB host galaxies. So like I said, Chime is really leading the way when it comes to FRB detections with over 3,000 FRBs detected to date. And starting next year, with the addition of outrigger telescopes to the array, they will localize every single FRB to a precision of about 50 milliarc seconds. And so we're expecting something like 1 to 3 precisely localized FRBs per day. And so this will completely change the field. Yes.
So, one thing you said that getting more localized. One of the things I sort of noticed seems to be, it doesn't seem to be a correlation between location of FRB, ghost galaxies, and some information. So doesn't this always sort of point to the delay time?
Well, I would argue that the sources in spiral arms, for example, would challenge the long delay time notion. But with larger samples, the kinds of things that we can start to do is, for example, adaptive optics to look at how offset the source is from the edge of the spiral arm, right? This has been done for supernovae, for example, and that actually does shed some more kind of detailed insight into the ages of progenitors. And I would say, the location of an FRB in a spiral arm is kind of the location of an FRB in a globular cluster. So I think we're at the point where the sample size is small enough that it's to draw any, sweeping conclusions. The other thing that I think will be really illuminating is how do the FRB properties themselves correlate with host galaxy type? Has not been done whatsoever. So, for example, the dispersion measures, the scattering, these polarization of bursts, do those sort of also correlate with the environment? We've actually seen that. So for the 2 and dwarf galaxies, Those are also interesting in that they have very large excess dispersion measures. So again, kind of painting a picture of a ton of material immediately around you.
Something or
Yes, exactly. Yeah, so hopefully we'll be able to, shed some light on this soon in the next few years. Okay, so that is most of what I want to say about fast radio bursts. I mentioned at the beginning of the talk that I do want to talk about radio transients more broadly. But before I do, I want to come back to these persistent radio sources that I think are really interesting. So again, these are repeating FRBs. They've both been localized to dwarf galaxies, and they are both coincident with persistent radio sources. Right, and again, the prevailing theory is that these radio sources are coming from some kind of magnetar nebulae. In other words, the emission is related to whatever's producing the FRB. But we also know that similar sources are definitely not ubiquitous in the sample of localized events. So this figure here is showing limits on the luminosity of a radio source as a function of redshift. And you can see in quite a few cases, we are now starting to probe luminosities well below the two known radio sources and finding no such counterparts. But the fact that we now have detected two of these FRBs in dwarf galaxies with persistent radio sources suggests that such sources may actually serve as signposts for FRBs in the wild. And this was the motivation of some of our work a couple of years back. So in 2020, Amy Reines and collaborators presented this discovery of 20 compact radio sources in dwarf galaxies. And they argued that the emission was coming from black holes, which have in some cases wandered from the centers of their host galaxies. Of course, we thought this combination of dwarf galaxy and persistent radio source was interesting for a different reason, namely the fact that they looked very similar to these two repeating FRBs. And so in our work, we set out to compare the properties of these radio sources to the repeating FRB. So things like the radioluminosities, host galaxy offsets, and so on. And what we suggest is that based on a sort of overall consistency in these properties, these compact radio sources may share a common origin with the repeating FRB. So this figure here is showing luminosities of the radio sources shown in red points as a function of their host galaxy offset compared to the first repeating FRB. In this case, the fact that they are somewhat less luminous, we think, points to an older evolutionary age of those systems. But based on somewhat comparable luminosities and also similar spectral energy distributions, again, we did argue that these sources are very similar to this first repeating FRB. So we've since obtained multi-frequency VLA observations of these sources in order to really try and pinpoint what is it that's producing the radio emission, right? Could it be some kind of magnetar nebulae, or are these AGN, as had been initially proposed? So this is work that's being led by Vic Dom at Northwestern. So stay tuned for those results. But the last thing that I want to mention in regards to this is that it really opens up an interesting prospect for an entirely new population of radio sources on the sky. So for many years, we've thought of the radio sky as being largely composed of star-forming galaxies and AGN. When you plot the number density of radio sources, you see these two populations clearly emerge. So AGN sort of dominate the source counts at higher luminosities. But it's clear from these two FRBs with persistent radio sources that there's a third population of radio sources out there. And we've actually already started to see hints of this. So separate from these FRBs, there have been a number of discoveries of long-lived radio transients in dwarf galaxies. So in surveys like the VLA Sky Survey and BERT. And then we've been conducting late-time follow-up of superluminous supernovae to look for these things. And in fact, this led to the first such detection. So I'll just say a little bit about that. I talked about superluminous supernovae a bit at the beginning of the talk, but the idea here is that the radio emission from these things would be coming from a nebula. You expect this emission on timescales of about a decade after the fact, because you need to wait for the supernova ejecta to become optically thin to radio emission. And these radio observations are really the only way of probing a magnetar, right? So we think that they're powered by magnetars, but a radio detection would really be a smoking gun signature. So we conducted the largest radio survey of superluminous supernovae to look for associated radio emission. As I said, this did lead to the first such detection shown in the and we argued in the paper that the properties of the radio source were in fact consistent with a magnetar origin. But the sample, we do not detect any radio emission. So this is showing light curves for various classes of transients. You can see gamma ray bursts up here, typical supernovae down here. And you can see our limits at very late times, which are starting to probe this new region of the radio transient phase space. So even with our limits, though, we can start to place some really interesting constraints on magnetar models. And so in particular, we can constrain relativistic jets. This is one prediction of magnetars. So here I'm showing the energy density phase space of a jet for different observer viewing angles. And the idea here is that a jet that is initially pointed away from you will decelerate and spread into your line of sight of late times. And so that's why we're really interested in looking at these things at late times on timescales of a decade or so. And here, each curve corresponds to a single supernova, where the region to the right of each curve is ruled out by our limit. And you can see that our limits are starting to probe the most energetic GRB jets. So we can at least rule out that region of the parameter space with our limits here. And again, I just want to emphasize that these radio observations of superluminous supernovae are really unique because it is kind of the only way we have indirect evidence through the optical. I would argue that these things are powered by magnetars, but the radio emission is directly probing magnetar nebulae. So it's a really unique probe of their progenitors. Okay, so that is superluminous supernovae. There's another reason why this very late time region of the parameter space for radio transients is interesting. And that's in the context of type 2 supernovae. So the idea here is that we want to understand the processes driving mass loss from these stars. We see in optical light curves of type 2 supernovae a huge diversity in these sources. This is telling us something about the final stages of stellar evolution. But if we want to really make progress in our understanding of these events, we want to observe them in the radio at very late timescales, where we're now sensitive to material that was ejected in the centuries before they exploded, right? So when we look in the optical, we're really just probing material in the immediate vicinity around the star. If we instead wait 100 years and point a radio telescope at it, we're now probing material much further out from the star. And so this is telling us about the mass loss history in the centuries before this event exploded. So we are currently conducting the first systematic search for late time radio emission from a sample of about 300 type 2 supernovae. And you can see, again, how we're starting to fill in this unique late time region of the radio transient phase space. Okay, so just returning to these radio sources in dwarf galaxies, as I mentioned, there's kind of growing evidence that these types of sources may constitute a new population of radio sources on the sky. And so we are interested in trying to uncover this population. The current number of these things is quite small. So there's something like 50 or so compact radio sources in dwarf galaxies. And one thing I want to point out here is that we think we're probing two really interesting populations of sources. So separate from these sources associated with fast radio bursts, we also think that there are these AGN in dwarf galaxies that I sort of alluded to. And these are interesting in their own right? So these are thought to be the seeds of supermassive black holes. In other words, we're probing intermediate mass black holes with these radio dwarf AGN. And this is really important when it comes to understanding the growth and evolution of supermassive black holes. And so in order to uncover a large population of these sources, we have a VLA large program starting next year to observe 1,700 dwarf galaxies in the nearby universe. And so hopefully we'll really start to build up a much larger sample of events and really start to understand these two very unique populations. Okay, so I think I'm close to time. So I'm not going to talk about CMB experiment. And I'm just going to jump to the conclusion. Okay, so I have conveyed why host galaxy studies are so important when it comes to transients more broadly, but certainly FRBs is still very early days, and so I think there's a lot to learn there, and hopefully that picture will become clear in the next few years. And then when it comes to radio transients more broadly, as you know, I think there's a lot of exciting work to explore these previously unexplored regions of the parameter space to potentially uncover entirely new populations of radio sources. Yeah, and I won't say anything about CMB surveys unless there are questions. Yeah, so thanks for your attention.
I mean, a bunch of CMB people who slides have quickly gone up, so it's not a good game.
I'm still confused about the new population of radio sources. What phase space? Are you talking about radio emission versus stellar mass? Or
Talking about,
or maybe your plot of radio luminosity, where do they live in that?
In terms of luminosity. Okay, so yeah, so these are 10 to the 28 to 10 to the 30 or so. So if we come back here, here they would occupy this region of luminosities. Time scale is a bit unknown because we don't really know yet. For example, the two FRBs and with persistent radio sources, we think we're probably catching those like decades after they went off. So time scale may be probing here. But the takeaway there is just the fact that these transient radio sources in dwarf galaxies are a long-lived population of radio sources that are not characterized by radio number count.
So you're saying there's another active phase.
Yeah.
Questions? Jill?
The radio sources. So you're saying they're not captured by the radio counts?
Yes, so the transient sources, yes.
But the persistent sources.
Well, we think those are transient. We think those are decade-long transients captured by the radio source count.
Wait, why would it be a source count that's done with snapshot in time?
Well, if they're evolving on as a function of time, then I guess they might, okay, you're right. They would show up in the radio source counts, but I guess the region of parameter space that we're probing that is new is radio sources in dwarf galaxies, is something that has not been explored.
There is this long-running excess radio background.
Yeah.
So someone holding new source is not captured by the number count. It's super for other reasons.
That is a fair point, yeah.
So I think I saw Deca, and then I think Brian also had one, so I'll do another. Deca, Brian.
I was curious about the preliminary spectra that you showed in the radio. I don't know if the spectra was peaked.
Yes.
And I thought that was interesting. I know that AGN can do that. Distinguishing AGN from the 9 power.
Yes.
Can the measure also create something like that?
Yes, it can, absolutely. So yeah, that's a great question. So I think you're referring to the word here. Yeah, so a magnetar certainly, the self-absorbed emission would be kind of a generic signature of some kind of compact nebulae. So yeah, so what working on now is some kind of equipartition modeling to get radius energy constraints out of that. Yeah.
That's one more question. Sure. So to another version, we're trying to constrain the delay time distribution of FRBs. Do you think that the delay time distribution of FRBs is different than the delay time of?
Is there any reason to think?
Like, should all magnetars be producing FRBs or
Oh, gotcha.
or is it?
Yes. I think it could be separate. So if there is a reason to think that, you know, FRBs are only emitted from a magnetar at some stage in its life, then I think that complicates. Yeah. And for example, from the known repeaters, we do see that they tend to be more active sometimes than others. So there's a duty cycle question that also comes into play.
Brian?
Yeah, thanks for your beautiful talk. So a couple of things. So in sort of analogy with gamma ray bursts, you might imagine, like, and you saw one of the cartoons that you drew of it, of beamed emission. Do we have any constraints on the beaming? And the slide here might answer the second thing is, would you expect afterglows, like, you know, interaction with the interstellar medium? And I guess this plot is sort of that, right?
Yes. So first question, I don't know off the top of my head what constraints have been done on beaming. I'm trying to think. I think the best constraints would come from, there are two sources, not to muddy the waters, but there are two sources that show periodicity in their active rate. I think there might have been some constraints with those. I don't know off the top of my head though. And your second question was about afterglow emission.
Right.
And yeah, so you mean if there's like some kind of supernova and you have an interaction with the supernova ejecta and the ISM?
Yeah, just in general, if it's beamed emission and then it's interacting with the interstellar medium, and then you can see, you know, at other wavelengths through that interaction.
Oh, you mean it? So I guess I'm confused about, are you saying if the FRB itself is interacting or if there's...
Yes, that's what I'm saying, yeah.
Oh, interesting. That is very interesting, and I don't know. I don't know the answer.
Yep. No, that's right. Cool. And then finally, I'll shut up, but polarization, is there any polarization information or expectations for what you would see?
Yeah, the short answer is that the polarization is all over the place from burst to burst. There are no clear differences between repeaters or non-repeaters. Some are highly polarized, others are not. Some show very high rotation measures, including the two in dwarf galaxies. Others show negligible rotation measures. So yes, there's polarization, but it is not particularly enlightening yet.
Cool, interesting, thanks.
My rotation measure question. I do have another question. So in analogy to like pulsars, do we learn anything by looking at repeating FRBs at different observing frequencies and seeing change in shape, or are they always changing shape, or I mean like full shape?
Yes, great question. And my annoying answer is going to be that some change shape, some don't change shape. Some are broadband, some are narrowband. Yeah, so that's kind of the obnoxious state of things. Yeah.
Okay.
Yes. Yeah, for now.
So if there's this sort of like general consensus that these are probably all magnetars, then oh wait, maybe they aren't. Like, what are some other formation mechanisms for FRBs?
Yeah. So for example, the globular cluster ones do invoke like white dwarf scenarios. There are some scenarios that also invoke like AGN. You know, you could have a pulsar that's near an AGN and a wind from the AGN. AGN acts like as the cone through the pulsar's magnetosphere, and that emits some coherent emission. If you want to go really deep, there are like cosmic string theories. Yeah, so yeah, I think I would say magnetars and some white dwarf models, but even the white dwarf models invoke magnetars formed in some manner. Yeah.
This is very helpful. If you modeling or want to be expected to be able to then take this done.
Yeah, so roughly decades to centuries, we think that these things will be active as emitters of both a persistent radio source. I'm sorry.
Yeah.
Oh yeah, as a persistent radio source. The duty cycle is a bit of a more open question, probably decades to centuries.
Source of these, I mean, by the way, so small minority cases. It's all magnified. Just being so star. That's really going
Yeah, I mean, I would agree. Yes. So that's part of, you know, you can look at the star formation histories of these galaxies and see if that's kind of broadly consistent. But again, I would probably like the globular cluster. It's a
sort of offset, like about one word. So it takes longer than it would take. Well, so what they kind of short eventually. What we learned from it also as well.
oh, so if the delay time is short and yet somehow it's still offset from what you're saying?
Yeah.
Oh, yeah. So typically the way it's treated in supernovae, you're looking at where within the spiral arm it's located to tell you something about the thing. You're saying not on spiral arm. Most of the ones where we have high resolution imaging, they are on the spiral arm. They're just not in the brightest. Yeah, so they're still in the spiral. Yes, yeah. There have been actually some really nice studies doing the, you know, like calculating the velocity of these things. Yeah, but we don't have that for a lot of sources because it's really hard to get that high resolution.
So all and then
because of the similarities with pulsar energy. Is there anything specifically that points to the strong specific polarization goals? Like, is there anything else?
So the rotation measure, I would say, is the other thing that's
So the maximum rotation measures.
yes, yeah. And there have been some work, or there has been some work looking at that. Yeah, so it's mostly the energy scale, trying to invoke very large magnetic fields to give you a much more energetic burst. Yeah.
I was just wondering why is there such a big focus on looking at galactic sources of FRBs rather than these galaxies? Because I would be thinking like it'd be easier to like, figure out the source or do like those stuff.
you should do that. Things. Find plus one.
Okay, sorry. There was one in the Milky Way, yeah. So the thing is, typically, if we detect a coherent radio emission from something in the galaxy, we think it's a pulsar or one of these RRATs, rapidly rotating anomalous. I don't remember. Yeah. Yeah, so the energy scale is just so vastly different. So there was this one event where we do detect a coherent radio burst with very high energy from a known galactic magnetar, and that was huge. That was a huge deal, and it is kind of telling us that maybe the luminosity distribution is like much more continuous. Like, you know, you have pulsars, and then this continuous distribution to magnetars. But yeah, otherwise they've not been detected. And it's kind of challenging too, because, you know, if you detect, yeah, I mean, I guess the luminosity would be the most telling thing. Yeah.
So when it comes to these repeaters that we have, you said the vast majority don't have any sort of periodicity to them. What mechanism would make these magnitude, it looked like it was the shocks that were actually causing the radio burst part. What mechanism would make that happen on a repeating scale with no periodicity? Or is there any consensus on what that?
Yeah, great question. And so the kind of general idea, if I can find that figure again, is you basically just have the magnetar that is flaring kind of sporadically, right? And it's just an FRB is emitted, it's random. There is no, it's not like a pulsar where, you know, it's a very periodic thing. It's just this kind of like random process. One thing I didn't talk about at all, because it just kind of further complicates the picture. We do know 2 FRBs are periodic in their cycle though. So it's not like a pulsar that, you know, it's got a 30 millisecond period. It's for one of them, it's a 16-day periodicity of a 4-day window. So every 16 days for 4 days, it's very active. Yeah. And in that case, like 16-day periodicity, so maybe some kind of, yeah, you have to invoke some kind of binary system, accretion of some kind. Yeah, but again, it's not like yeah, regular periodicity, if that makes sense. Yeah.
Looking forward.
One more question. People.
Is the
The active period. So for the 16-day one, it's like a 4-day window where you just detect a ton of bursts, and then it's quiet for 16 days, and then 4 days you detect a ton of bursts.
Just two here.
Oh no, it's been observed for years now. Yeah, so for years. And then there's another one that, depending on who you talk to, tell you that there's a 160-day period in its activity window, but that one's a little less robust because we have not known if it's
I think that's a lot harder to do.
So I'm sure there are more questions for us because clearly we can't. But we must give her a little break to recover before dinner. This is the last colloquium of the semester, so I do hope a lot of you will join us for dinner. But next time, Tarraneh again. We all interested in dinner because we actually have a special seminar speaker this afternoon as well. We'll have a twofer, so joint dinner with Yon Senting and Tarraneh. And because of logistical constraints, she picked Italian, he picked someplace close to the department. So we'll go to Tarraneh's and we'll meet in the lobby at 5:30. Thank you, folks.